Okay, cool. So hi guys, this is just a little thing that I prepared for that tat. Just very basic stuff. That had a nice little derivation for work that I wanted to share, so I thought I'd just make a video to share it. Um, yeah, so just a little revision. This is obviously chapter 7 in the Green Book. We're dealing with transducers, which are like the interaction between electrical energy and physical, like mechanical outputs. That is your kind of transducer. And in the one way it's a sensor, and in the reverse way it's an actuator. Okay, so that's cool. There's some examples. You can give examples of transducers like solenoids, whatever you want, like a microphone or a speaker, very similar. That's what shows this forwards and backwards really well, because they're very similar things, pretty much the same thing. Yeah, I'm just speaking about it quickly because I'm just going to do all of this very quickly because it's like revision. We have in the one direction we have electrical energy, then you couple that energy into a field, and then you make a mechanical output. So this is if you're going from electrical to mechanical. This is like your actuator. So like a motor is an example of this. And it's just showing that in each of these steps you have losses. So in electrical energy you have resistive, then the magnetic core losses, and then friction losses. And then in reverse the same thing happens. So that's exactly what, and they're showing from which system. So that's exactly what this diagram is saying. You have that from a mechanical system, and you have losses in each of the systems, and there's the various names. So yeah, here's magnetic circuits. Just a quick, because obviously when we're doing all of our transducers, you'd notice by now that they are just magnetic circuits. We're going to have some sort of magnetic field that's going to be producing some form of a force. So yeah, we interacting between those two things, but to start we just need to make sure that we understand our magnetic circuits. So yeah, this is if we can derive this sort of relationship with the flux between the two of them, that they actually behave in a similar sort of way with MMF, reluctance, and flux within their equivalents over here. I just always like to show these foundational relationships and then a derived relationship over here. So it's just like for your voltage, your MMF, it's Ni is equal to HL. That's your number of currents is equal to the path, the length times by the magnetic field intensity. So that is Ampere's law. If you ever see this in the integral form, which you will see with Maxwell's equations and stuff, this is what it is. So that's current density, that's the surface integral. This is like how aligned, because these are dot products. This is dot with the surface though, this is a closed surface. This is like Stokes' theorem. So if you've done that in maths as well, it just gives it the reality. Very beautiful stuff. Check that out deeper. But yeah, so there, that's all you're doing. You're just saying that this times by the length, magnetic intensity times by the length, is equal to the number of current intercepts that you have. Okay, so yeah, there we go. Then we just have a basic definition of magnetic flux, which is like takes into account the area. These are very simple versions of it, but yeah, so you just have area. So if it was just perpendicular, so if you could have angles, then maybe from high school you'll know it's like cos theta. If it's at a slight angle, it's like how strong your sail in the wind. Then you have this intensity, which is kind of you're relating the field, the field to the material. So that's kind of like permittivity with the electric field, but now we have permeability for the magnetic field. And then you can just have a derived sort of thing, sort of quantity like resistance in a way, but we're going to call it reluctance, which is the ratio of MMF to the the flux. And then if you actually do that division from these ones, which are I think quite obvious, like this is very obvious, this is very obvious, this one is just a simplification of this, and then if you divide these two, knowing that you can relate B with U, then you get this. So now you have kind of geometric and material properties to describe what is actually going to be the relationship of these two things, of MMF and flux. So cool, yeah. So then that's just a basis just so that you can make your magnetic circuits and just feel comfortable with that and know where all the formulas are. Maybe even for the subconscious it will just be happier. So now we're going to speak about magnetic energy, because we're actually going to have some conversion of energy. This is how we're going to produce a force. The concept of energy is a very beautiful thing. You should look it up. Go look up Joule, the guy who actually did it. and they were relating that there was this kind of this thing, this energy. Like, what is energy? It's like this conservation sort of quantity that you could actually it wasn't standardized before, but you could say, like, if I heat something up a certain amount, that's equivalent to moving something of a certain mass a certain distance. There was this quantity that you can relate those two things. So that was Joule's work. Why it is joules. That's very interesting. You should see all the units, how you can relate everything. Very useful thing. So yeah, we're going to look at magnetic energy, because basically we're going to derive that reluctance equation that you use, that you see. You're going to do like the derivative of reluctance. Why do we do the derivative of reluctance? It might seem very arbitrary and a formula to remember, but that's where I want to come in here and make that easier. So we're just going to start with inductance, because an inductor is, remember, it's those coils making a magnetic field. And we're just going to do this basic relationship, because I think we're all kind of comfortable with this sort of relationship. And we're going to basically, with this voltage and differential current, we're going to find the power. Because remember, you're also familiar with this, that V times by I is your power. It's not just your voltage that's important, it's your voltage and your current. So you times those two together and you get power. What is power? Power is kind of like the derivative of energy. That's why when you say like power times by time, it's the instantaneous sort of impulse of energy, but then it happens over a duration. So you times it by time. That's essentially integrating, so your time could actually vary in whatever functional way if these were values of time. If they're not values of time, then it would be like a simple multiplication, but we're going to do it with the integral. And then here we go. Remember, it's the same things that we have here. We're integrating it. Cool. And then we end up with this. Okay. This is the energy stored in the magnetic field. We have current and an inductance. If you ever want to know what inductance is, it's very a lot to do with current and relating current to magnetic fields. That's kind of what inductance is doing, but you'll see later when you have like a flux linkage, which I do mention a bit later. So there we go. Hope that this part is fine. We get to this. E is equal to half Li squared. Kind of, you see this Li squared, it's a bit similar to like half mv squared, isn't it? Okay, but now there's L, so but instead of mass we have like inductance. Interesting. So yeah, how do we relate force to energy? This is cool because I don't know, we have done this in physics, where you just like say, well, force times by distance. If we have a force acting on an object that goes a distance, that's the energy. Okay, so it's actually the integral, because this is when you do simplifications of like integration, you just times. You know what I mean? It doesn't vary. But yeah, we made this is the more advanced definition, where we actually integrating it. So if you do the integration of force in the direction that you're concerned with, or the direction that it's going, then you get the energy. So I bet you didn't know that you could relate energy and force like that. But it is actually very important to know that. So yeah, so we can say force is equal to the derivative of energy by doing the reverse, because if you differentiate. Because I think that's actually called the fundamental theorem of calculus. So it actually took me a while to realize that's actually what it was, but this is, I'm pretty sure, the fundamental theorem, I think, where you can relate between integration and differentiation. But anyway, this is a fun little problem. This is actually one of the reasons why I wanted to share this video, is that if you do the derivative of energy, okay, we should get force, okay? But this is a very cool exercise to try differentiate kinetic energy with respect to displacement, not time, displacement, okay? I made an error here. I actually sat with a friend and we spent a while to try to figure this out, because there's actually something wrong with what I'm saying here, that you could just say MA. You'll see with like composite sort of like chain rule doesn't work out. There's a bit of more depth to that. So please try and do this. Try get from kinetic energy to MA, force. From kinetic energy derivative to force. Okay, just try do that. And remember, it's your x derivative. But anyway, so then we'll know that force, back to this magnetic field energy, how much energy is stored in the magnetic field, it will be the derivative of that, okay, with respect to x. Very important. which makes sense because it's the force times by distance, remember, with the integral. So just a reminder, our flux linkage is equal to current times by inductance. We can solve this. Remember, your flux linkage is kind of just your number of flux turns, because there's a many turns, when that's like kind of like with your transformers when you coil your wire. It's like a gear in a way. Gear ratios, okay, whatever. So there we go, we can solve that. That inductance is equal to this. We look again at reluctance as the ratio of these two things, like voltage is the ratio, well, this would actually be resistance is the ratio of voltage to current, but yeah, it's mmf and flux, and that's Ni and flux. Okay, cool, we can solve for current. We get this with reluctance, sure. Now what we're going to do is we're going to basically substitute these into this formula here, okay, these quantities that we found here. So we're going to first do it for the inductance. We replace the inductance by this. There's still the I squared. Here's our I over here. We're going to replace this over here with the reluctance. We're going to pull it in, and then what's going to happen? Boom, we're going to actually cancel out some stuff, get a square, and we're going to have a reluctance and a half. And then this is it. So half Li squared is actually, this is the magnetic field energy, is the same as this quantity here with reluctance. Now your reluctance can actually be a function of x, which is what we saw from last week, where if you have like your like arm that's moving, like this sort of thing, like we say you're going to move this bar up and down, that means you're going to change the reluctance, and that's going to relate to energy. So you're going to create a force, and it's going to relate to the energy stored in that field. Okay. So yeah, this is how you get to that formula. This is a function of x, reluctance. Everything could be a function of x, but we're just going to say reluctance is a function of x. And there we go. So this is what you've been doing. You've always find that you have to do the differential with respect to x of the reluctance, and this is why. It's the same. It's the same as like doing the integration of force, force times by distance, to find energy, but now we're actually going to find the force. So there we go. Cool. And then yeah, that's like pretty much it. You can expand it out where there's the L here, you see, so in this sort of circuit where we have this distance x, then we're going to, you can relate that, you see, your L would be your x, and then now your R is a function of x, and there we go. And then with that you could do some examples, but yeah, I hope that makes a bit of sense for the derivation. Hopefully I didn't go too fast. I also didn't want it to be too long, then you probably won't even watch it. Try this out for fun if you have some time. I don't know if you all have time, but it's cool to see if you understand these types of differentials with respect to x and things like that. It's actually not as complicated as it seems, but it took me a bit of a time to do it. So yeah, there we go. Magnetic energy. Remember, where was it? Force. This is a fundamental relationship, energy and force. That's very cool. And there we go, that's magnetic energy. And then we did the conversion to make it actually in terms of reluctance. So now at least you can know why we use this formula and why we derive it to find force. So good luck, everyone. I hope that wasn't too long.